Hello, and welcome back to EECS 367, Introduction to Autonomous Robotics, and Robotics 320, Robot Operating Systems. This is our sixth lecture of the semester. Today we're going to be talking about linear algebra. So we're going to go over a bit of a refresher over some kind of basic and core topics within linear algebra that will prepare us for our upcoming projects and our upcoming discussions and lectures on kinematics, so forward kinematics and inverse kinematics, which are going to be relying heavily on some kind of foundational concepts from linear algebra. So before we get started, let me go ahead and minimize myself so we can all see the slides. All right. So to get started today, let's talk about the reason it is that we're going to be using linear algebra and how it's going to factor into that notion of kinematics. So as a bit of a refresher, if you remember from a few lectures ago when we were talking about the configuration space of robots and this high-level idea of coordinate frames, one of the things that you'll remember, right, is that we describe each of our robots with a set of rigid body links, where each of these rigid body links are then connected to various joints, but crucially, each one of these rigid bodies is defined with respect to its own coordinate system, right? So in other words, like another way of kind of saying that would be that each rigid body has some notion of a kind of local space that's defined with respect to some local origin. So in the figure here, these pink cubes could be thought of as, let's say, a rigid body, like one link of a robot, and the axes then, the red, green, and blue axes are defining the origin of the local coordinate space for each one of these two links. And so in addition to this then, we discussed how in these upcoming projects what we're going to be considering is how these rigid bodies are connected by joints, and how these joints then are what allow actuation, right? So each joint will have associated with it some motor that can exert force to affect the corresponding degree of freedom that aligns with that joint. So in the case of hinge joints, right, so there's this rotational degree of freedom, or in prismatic joints where the joint can translate, there's this translational degree of freedom. But ultimately what we're going to have to do to model these systems is we're going to have to know how to relate these rigid body links as they're sort of dynamically moving with respect to one another, as caused by the motor controlling this, the degrees of freedom, or the joints. And so the way that we're going to be modeling those relationships is using linear algebra, with the technique known as matrix transformations, in order to transform the coordinate systems between these various rigid bodies and joints. And so it's within these matrix operations that we're going to be modeling the spatial geometry of these links, and also modeling then how the joints are affecting the links' spatial relationships. And so once again, so just as a bit of a refresher, so to cover, again, like a couple lectures ago, we discussed kinematics and dynamics, and so the reason that these matrix transformations are going to really be useful is within kinematics, especially, at least as we first started to get into kinematics and dynamics. And so once again, when we're looking at these robots that are collections of rigid body links, like the humanoid robots, for example, shown on this slide, they're comprised of these joints, which correspond to degrees of freedom that the robot can be manipulated according to. And so these degrees of freedom are kind of described by translation or rotation axes for individual parts within the system. And so as we try and model those degrees of freedom, the first thing that we're going to be trying to model are these kinematics. So that is essentially defining the set of configurations that are valid, that the robot can take and still obey its constraints as defined by the degrees of freedom, right? So basically ensuring that the robot stays together, but that the various joints are articulated in a fashion that is valid according to the joints within the kinematic structure of the robot. And so this is what we refer to as robot kinematics. And so the goal of this topic of robot kinematics is going to be essentially given some description of a robot structure. So in this case, figure here, we're looking specifically at a robot arm. We want to be able to compute two kind of core pieces of information. So the first is what's called forward kinematics, where again we're given this structural description of the robot arm, so the state of the robot arm at a specific time, and we want to be able to infer the pose of the end effector of that robot given each of the corresponding joint states, right? And so we want to describe the pose of the end effector with respect to a global coordinate frame. So like in the space of the world itself. And so to do that, we have to relate the pose of the end effector locally to its own coordinate space to each one of the links and each one of the joints along this robotic arm, all the way back to the base joint and the base link, which are defined with respect to the global coordinate frame. And so we're gonna talk more about this, but that's just setting up this idea, right? So forward kinematics is just setting up this idea that we want to be able to infer the pose in global coordinate space of the end effector. The second topic, which we'll be talking about after forward kinematics, is what's referred to as inverse kinematics. And so in inverse kinematics, you sort of go the opposite direction. You'd say, given some pose of the end effector which would be desired, what joint states does the robot need to take in order to reach that desired end effector pose? And so we're going to be talking about that after we talk about forward kinematics. But before we can talk about and go into the nitty gritty details of either of these two topics, we're going to have to do a little bit of a refresher on linear algebra, because both of these forward kinematics and inverse kinematics are based on these transformations between coordinate spaces, which we're going to again be representing using linear algebra. And so before we start talking about these matrix transformations, to help with like a little bit of visual intuition, this particular diagram can help with a sort of a mental model for the type of degrees of freedom that we typically consider in our robots, in both a 2D case and then converting that to a more complicated 3D case, just to help kind of picture what it is we're thinking about when we describe degrees of freedom. Right, so in the first column, we have a revolute joint in a two-dimensional space and then a three-dimensional space, right? So this is just a joint that will connect two links and allows those two links to rotate about one another according to some fixed rotational axis. And then in the second column, we have our prismatic joints, right? So once again, these are joints that connect two links, and these allow translational motion of two links with respect to one another. And so we looked in some past lectures, right? And as you're starting to work on your pendulum arm now, we looked at this sort of two-link arm that has two rotational degrees of freedom, and so the two links are able to rotate about one another and also rotate about the global origin. And so one then physical example of a two-link arm that we talked about was the scar arm. And so with the exception of an added kind of prismatic end effector, this is an example of a real robotic system that is really based on this two-link kind of pendulum structure, where there's two revolute joints, so one connecting the robot to the base, and then another that is at that kind of elbow joint that allows the robot arm to rotate about its workspace. And so we can see here in this case that this particular structure is pretty effective for allowing manipulation tasks within a confined workspace. But there are additional examples of these sort of two-link arms. So this one is a little bit more complicated. It has an additional rotational joint at its end effector and also at its base that allows it to rotate about space. But you can see in this particular case, this Motoman robot is performing some kind of mechanical manipulation tasks, and is doing that by, again, manipulating these degrees of freedom in order to control its end effector. So another example, which we haven't seen up to this point, is an example from the MIT Leg Lab. So this was a biped hopper robot. So this was a sort of an early precursor to some of the bipedal robots that you might see around campus today. where this particular robot is able to, you can see here, to sort of run and hop and jump as it moves through space. But at the end of the day, this robot once again has a set of rigid body links, right? So the legs, for example, are rigid bodies that are connected to rotational joints, and also there's some prismatic joints within the base of the robot that allows it to perform these hopping actions. So that, more recently you might be familiar with some of Boston Dynamics robots, where again these can be described in terms of their degrees of freedom, where there's degrees of freedom within the leg and also within the base that attaches the leg, that allows for revolute motion of the leg joints, and ultimately allows some of the behavior that you've probably seen from some of the popular videos that they post. So another example then that you're probably familiar with is quadcopters. So in this case, there's no translational joints, but in a sort of standard quadcopter, you'd have 4 rotational joints, right? So each of the motors is connected to a propeller, and that propeller then sort of revolves rapidly, which leads to propulsion, allowing the quadcopter to fly. And so that's another example of how these configuration spaces with respect to degrees of freedom really do kind of apply across the different types of robotic systems that we think about. This particular video is a really cool example of just how effective quadcopters can be in terms of their sort of precise control. And so some of the topics we talked about on control would really apply here, where you need a controller that can react really, really fast in these cases, where, right, there's really no like sort of lag time. Like there's really no time here where the controller, when it's doing these acrobatic movements, could sort of wait and have to process, right? It really needs to process in real time. Otherwise the overall system will not be effective in some of these maneuvers. And so if you're curious, the video link is here for this particular demonstration, but they've done some really nice work in this lab on controlling these acrobatic robots in the air and actually kind of coordinating their actions. So you'll see here some coordination between the two, where they'll attempt to catch the pole with the second quadcopter. Let's see. There we go. And so once again, ultimately what the configuration space for these robots can be thought of is in terms of these rotational degrees of freedom, and also in this case, the global translational degree of freedom about where the robot is, spatially within the global scene. And so right. So this is ultimately, this question of kinematics is motivating how it is we can express the state of an articulated system, kind of completely, right? So there's this set of individual parts within a robot, and we want to understand how can we describe this collection of parts in a way where the relationships between the parts in space are being represented accurately. And so this is what we're going to be talking about as we get into forward kinematics and inverse kinematics. But for today's lecture, we're going to kind of go over some background linear algebra that we'll need in order to be able to describe these articulated systems. So when we think about linear algebra, the first thing that we can sort of think about is the foundational concept of algebra. So one thing that I would sort of ask as we start to think about linear algebra is this question of what does algebra itself as a branch of mathematics provide beyond just arithmetic, right? So when we think about arithmetic, we're thinking about just manipulating numbers with rules. But algebra is a sort of broader branch of mathematics that has an important distinction. And so it's worth thinking about that for a moment. And so once you've maybe thought about it for a little bit, here's how we might be able to kind of summarize what algebra provides, right? So arithmetic really is just the topic of manipulating numbers with defined rules, right? So addition and multiplication, for example, would be operations that arithmetic would would allow you to apply to known numbers. And what algebra gives us is the ability to abstract away the knowledge of specific numbers by using variables in their place, and still letting us use the rules of arithmetic to manipulate what now become sort of these symbols for representing variables. And so when we have numbers that are unknown, or we have expressions that we want to be able to take on more than one particular value, algebra gives us the tools in the form of variables to actually apply arithmetic to these sorts of mathematical expressions. And so, for example, right, so on the lower half, right, we have this example of x squared equals 5x minus 6. So in this particular equation, x is a variable. So x is not a known number. It hasn't been fixed. And so as a result of that, we can apply rules of arithmetic to ultimately arrive at a set of solutions, right? So in this particular case, x equals 2 or x equals 3 would both satisfy the original equation of x squared equals 5x minus 6. And so this is where algebra is useful, and this is where algebra extends the more kind of rudimentary standard arithmetic, right? So it allows us to operate with variables. So given that that's what algebra is providing, what then is linear algebra providing beyond just algebra? And so linear algebra is sort of the subset of algebra which is concerned with vector spaces, and in particular with linear mappings within vector spaces. And for our purposes, linear algebra is useful because it allows us to model complex systems efficiently. And so in particular, so within engineering broadly, but within robotics as well, many complex systems we can approximate to an acceptable degree using a set of linear equations. And so this is why we're going to be talking about linear algebra. And so when we say that linear algebra provides linear mappings over vector spaces, what we mean by a vector space is the following. So you can think of a vector space as being essentially a set of objects which are vectors, and defined over this set of vectors are operations that have to respect have to be closed under both addition and scalar multiplication. And so what that means is that within a vector space, there's going to be two operations which are essentially adding and scalar multiplication, such that if you add any two elements from a vector space, your output will be another element from the vector space. And similarly, if you multiply an element from the vector space by a scalar, your output will again be an element from this vector space. And so that's what we mean by closed with respect to. It just means that when you apply these operations to elements from the space, the output is guaranteed to be another element from the space. And so this will look probably familiar if you've worked with linear algebra before. So these two operations are defined on the left column. So we have addition and scalar multiplication, and then across the row, what we're illustrating is how basic arithmetic differs from algebra, which then differs from linear algebra. So if we start with the case of just the abstraction itself, right? So arithmetic. So in this first row, arithmetic provides no abstraction, right? Where arithmetic just defines operating on known numbers, whereas algebra allows us to abstract unknown quantities, right? So in algebra, we could have a variable x, which could take on a particular value like 3, but it could also be left as an unknown variable, an unknown symbol representing this unknown variable. Linear algebra, on the other hand, is going to treat x as a vector. So in our notation here, this column vector in the upper right cell of this table is describing x, this unknown variable, as a column vector that takes on this specific value, in this case, of this three element vector. So moving down then, so how the addition operation differs between these different branches of mathematics. So within arithmetic, addition is defined as you're familiar with, right? So it's just operating on known quantities to produce some output scalar. Within algebra, we can use our unknown variable within the addition operation. And similarly, within linear algebra, we can apply addition as being an operator on two elements from this vector space, where the output again is going to be an element from the vector space. So in the cell for addition under linear algebra, you can see we're adding this variable x with a known vector, and the result is then an output vector from the vector space. Finally, then, scalar multiplication. Again, so for arithmetic, scalar multiplication is defined how you're familiar with. We're just taking two known numbers, multiplying them, and we get out a scalar. Within algebra, again, we can use our variable and still define this operation on the variable. And then finally, in linear algebra, the distinction is that this variable is an element from a vector space, and so the output of this scalar multiplication operation is going to also be an element from the vector space, which in these examples, once again, is just this three-dimensional vector. We would call it this column vector. So why are we concerned with linear algebra? So as I was sort of saying a couple slides ago, many complex systems that exist within engineering problems, but also specifically within robotics, can be described by collections of linear equations. And so typically these will be approximations of the nonlinear system, but these approximations work to an acceptable degree, or to an accuracy that we can ultimately use for our engineering systems. And so within that, right, so algebra of scalars, vectors, and matrices is what's going to allow us to then model these complex systems and to do it computationally, right? And so by manipulating these groups of unknown parameters, we can treat it just like we're manipulating numbers within our computing devices. And so this is going to be essential for us as we represent frames of reference, so the coordinate frames that we were talking about in the case of rigid body links and joints, and also useful for representing rotation, translation, and sort of the pose, what we might say, of objects in space. So just to highlight, so the breakdown for our course, so the primary focus for AutoRob is going to be using linear algebra to represent geometry. So we're going to be focusing on vectors, matrices, basic, essentially addition, matrix multiplication, and scalar multiplication. So on matrices and vectors. So we're going to be considering essentially in geometry there's going to be lines, planes, and transformations of them. And so within that, then a second topic which is going to be used within this course is going to be solving linear systems, right? So once we get to inverse kinematics, we're going to be attempting to solve a linear system in order to calculate which joint angles will satisfy a desired end effector position, where that desired end effector position is expressed as a linear system. And so to do that, what we're going to be using is some of the techniques described on this particular slide. So nonlinear least squares regression, gradient descent, and topics such as those, which we'll talk about in today's lecture, and we'll talk about more once we get to inverse kinematics. And then we'll talk a little bit today, and we'll use just a little bit from what we call the spectral story. So there's going to be eigensystems, so eigendecomposition, eigenvalues of matrices, but the primary two are really the first two. So it's particularly geometry of linear algebra, how linear algebra can represent lines and planes in space and transformations of them, and then how we can solve linear systems. Okay, so to start to kind of go into a little bit more detail, so let's talk about these systems of linear equations that we're going to be using. So within linear algebra, we can describe a set of linear equations like the ones that are shown here. So by linear equation, what we mean is any equation that takes a form similar to the one shown on the slide here, where we have the summation of a scalar multiplication of a set of unknown variables being equated to some term, right? So for example, in the first equation shown here, right, so we have 3x plus 2y minus z is equal to 1. So in this case, we have three unknown variables, each one is being multiplied by some scalar, right? So 3 times x, 2 times y, negative 1 times z. And then the summation of those scalar multiplies is equated to this value 1. All right, so whenever we say a linear equation or a linear system of equations, we're talking about equations that follow that basic form. And so within this, right, because we have used unknown variables within this particular set of equations could be solved by could be solved by a specific configuration of these x, y, and z variables, or it could be solved by multiple. And so in this particular case, it might be useful just to see if you can work it out by hand. So maybe you can pause here if you want to try working this out by hand using just concepts from algebra. But if not, right, I'll sort of present the solution here. So this particular set of equations is solved by the following settings for the variables, right? So x equals 1, y equals negative 2, z equals negative 2. So if you plug these into the equation, you'll find that the equality statements are satisfied. And so how we're though going to express linear algebra for this course is by using matrix notation. And so this same linear system can be expressed in matrix notation as is shown on the lower part of this slide here. So what we can do is we can express our unknown variables as a vector which we call x, the scalar multiply parameters in a matrix which we call A, and then the known parameters that are on the right hand side of the equation statements can be defined as a vector which we call B. And so ultimately this set of linear equations can be described as the matrix multiply of A times x being equal to B, right? So in other words, then if the particular parameters then are shown on the lower right hand side of this slide, and so in this particular case, we're gonna kind of look at this linear system and walk through how the operations from linear algebra are applied in order to ensure that this matrix notation correctly sets up our linear system of equations. So within this matrix notation, the way to read it is we have this matrix A. Okay, and so this matrix A, you can think about each row of the matrix A as defining one linear equation. And so within that then, the vector x describes our set of n unknown parameters which we're going to want to solve for. Right? And so this equation then that's described by A times x being equal to B is actually describing what you can think of as a hyperplane in some n-dimensional space, where once again, n is the number of unknown variables that we are trying to solve for. And so depending on the number of linear equations and the number of unknown variables, this particular linear system will either be solvable or potentially it will not have any valid solutions. And so the way then that we can think about that is we can actually decide in certain cases when a linear system is solvable or not simply based on the number of linear equations within the system and the number of unknowns that we're trying to find. So there's a set of rules that we can use when we're trying to decide if a particular linear system is solvable. And so this first set of rules that we have here are going to be using those properties of the number of equations versus the number of unknowns. And so to start with, right, so we have the answer to each of these cases blocked, so that if you want, you could pause the video here and you could take a little bit of time to see if you can sort of think through it, or if you're familiar with some linear algebra background, maybe you can pause and kind of quiz yourself to see if you can remember. But we're going to start to step through these and describe some intuition about each one. So in the case where the number of unknowns is greater than the number of equations, this would be what's called a underdetermined system, which usually corresponds to an infinite set of solutions that would satisfy the linear equations. If the number of unknowns is less than the number of equations that are defined within the system, then we would call this an overdetermined system, which usually has no solutions that would satisfy each of the equations. And finally, if the number of unknowns is exactly equal to the number of equations, this would be a case where there would be a single unique solution. And so to try and build some intuition, what we'll do is we'll look at a couple of examples of these systems and try and visualize what a solution would really mean. So let's start with a 2D example where we're plotting here the two lines, the red and the blue line, are denoting each one is denoting a single linear equation. And so the collection then of the two plotted together, you can think about as being one of the essentially the equation that's implemented by that matrix operation that we saw on the last slide, just with two rows in the matrix A, right? One for each of these lines instead of three. And so within this plot, you can see that the lines intersect at this point 2, 3. And so what that is actually indicating in this visual sense is that the intersection of those 2 points would be a solution to the linear system of equations. And so if you were to plug in 2, 3 into both equations, you would have a valid equality, right? And so that's what in this case we have two linear equations and we have 2 unknowns. So we have x is one unknown, y is a second unknown. So in this particular case, there's a single solution because the lines intersect, and it's that point of intersection that is the single solution to the linear set of equations, right? And so in this particular case, the lines will only intersect at a single point. There won't ever be another point where the intersection occurs, or where there's a solution to the set of equations, right? And so another way then that we could build up some more intuition is we could consider the case where we have maybe different numbers of equations. So on the left-hand side of the plot, we're showing a case where we have just a single equation. And so in this case, there would be 2 unknowns. There'd still be an x and a y, and we have 1 equation. And so in this case, we have a system where there's an infinite number of solutions to this linear system, right? So any point along this line would be would result in a valid equality within the linear equation. So we'd have an infinite number of potential solutions. All right, so in the middle column was the case we looked at on the last slide, where we have 2 equations and 2 unknowns. So you can think about that as 2 lines, and then the x and the y variable are the 2 unknowns. And so in this case, the lines intersect, so we have a single point that satisfies both equations. And then on the right-hand side, we're sort of stepping it up a little bit, where we have 3 equations. And in this particular case, the 3 lines don't all intersect at a shared point. And so in this particular case, there's actually no point that will satisfy all 3 of the equations. And so for this particular case, this linear system would have no solutions. There'd be no single point that would result in a valid equality for all 3 of the equations. And so the one nice property about linear algebra is that it can work in higher dimensional spaces in addition to 1 or 2 dimensional spaces. And so what that looks like is when we said a couple slides ago that these linear equations can each be thought of as a hyperplane in some n-dimensional space, this particular slide is showing what a hyperplane would look like in a 3-dimensional space, where we have three linear equations being shown. Right? So each linear equation in a 3-dimensional space defines a plane, and so within that, then that same kind of intuition that we had in the case of lines in the 2D example would work for planes. So if there's a point that on these set of planes that intersects with all of the planes defining this linear system, then that point would be a valid solution. So in this particular case, there happens to be a single point that intersects with all 3 planes shown in this linear system. And so we would consider that single point to be a solution that satisfies all 3 of the equations. But again, we can also have cases in these higher dimensions where there are either infinite number of solutions. So on this particular slide, the 2 planes intersect and they form a line in 3-dimensional space. So any point along that line would be a valid solution to the linear system. But there could also be cases in three-dimensional space where the planes don't intersect ever, right? You can think about two planes that are parallel to each other, for example, and that would be an example of a linear system with no valid solutions. And so this visualization is just meant to sort of build up some intuition, right? So ultimately what we're going to need to have are computational tools that we can use for finding solutions to these systems that don't rely just on visual inspection. But as we're sort of starting to just talk about like a refresher of some of these topics, the visual intuition is really useful for our ability to really understand what it is that we're working with. So now that we have this intuition about vector spaces and linear systems, let's transition and start to look at how we can define our coordinate spaces as linear equations within vector spaces. So to start, let's look at a 2D example of a coordinate space, and let's start to consider how that maps to a vector space and then to linear system of equations. So in this particular slide, what we're looking at is a two-dimensional space. So in this figure, we have a horizontal direction and a vertical direction. And so there's this global two-dimensional space. And within it, then, we define two coordinate frames, which are given by these points O0, where my cursor is here, and also O1. And so these two coordinate frames describe then a sort of a local frame of reference within this global two-dimensional space. And so also within the global space is a particular point. So this point P exists within the global space, but it can be defined with respect to either of the frames of reference. So this point P can be described with respect to origin 0, which would be represented by this vector translation from origin 0 to point P, which is called V1, or point P could be described with respect to the coordinate frame at origin 1, right? And so that would be described by this vector translation V2. And so the thing to remember then is that these points within coordinate space, they exist in a global space, but they can be defined with respect to local frames of reference. And so based on the local frame of reference then, the points representation, right? So in this case, it's these two vectors that are representing this point P. They'll be different depending on the local coordinate frame's origin. And so a few other things then that are important to remember. So the first thing is, so when we talk about vectors with respect to these coordinate spaces, vectors will always have a direction with respect to their local origin, and also a magnitude, which is the length of the vector. And so what these vectors can be thought of representing is a translation from that origin of the coordinate frame to some particular point within the space. And so another important detail to think about with vectors is that they can be converted between coordinate frames. And so what that looks like, so on the slide here, what we're showing is what this vector V1, so the direction and the magnitude of V1, how it would be represented with respect to origin 0, which is in the first equation here. So V1 in the coordinate frame 0 is what this notation is denoting. That is equal to this translation vector, 5 units in the x direction and 6 units in the y direction, right? And so you have 5 units along the horizontal, 6 units along the vertical, and that describes V1 with respect to this origin 0. But that same direction and magnitude can be described with respect to the coordinate frame O1 that we were looking at, which would have then a different translation. So if we visualize what that would look like, so we're showing now on this slide these sets of transformed vectors with respect to each of the two coordinate frames. So that vector V1, which has this global direction and global magnitude in the coordinate space, can be also defined, as I'm kind of pointing to here, with respect to origin 1. Okay, so again, the direction and the magnitude is the same as our original V1, but it's been transformed to be defined with respect to origin 1, and so correspondingly, its definition here is different. And so it's always important to remember that when you're operating on vectors, so for example, if you want to do vector addition, or you want to compare vectors, for example, you want to be sure that you're working with vectors that are expressed within the same coordinate frame, because if they're not expressed within the same coordinate frame, then it's possible that the operation you're doing will not produce a meaningful result, or it might not produce a result you're intending for it to produce. At least in this class, as we sort of work in these coordinate spaces for the poses of robots, and so within that, then, so one thing you're probably noticing is our notation and our description for these vectors. So in this course, and as is typical in linear algebra, we express an n-dimensional vector as a column vector. So we would describe this x vector as this column vector that has then individual elements within it. So you'd have x sub 1 through x sub n, right, to denote that there's n individual elements within this vector. And similarly, we define matrices using this bracket notation, where the individual elements within the matrix are expressed in row and column form. So in this case, an m by n matrix will have m rows and then n columns, and so that's expressed in this rectangular matrix in this fashion. And so vectors, once again, are defined as a direction and a magnitude. And so what that would look like in our JavaScript code would be a multi-dimensional array, so an array of arrays. So in this particular case, if we wanted to describe the vector that has 2 units of translation along the horizontal direction and 3 units of translation along the vertical direction, we could express that in JavaScript using this variable a, which is an array of arrays, right? So this is to express in this case, a 2-dimensional vector. Similarly, for a 3-dimensional vector, we can extend that array of arrays by adding an additional element. So in this case, if we have some vector that has, let's say, a horizontal component in x, a vertical component in y, and maybe we could say like depth component in z, we can express that in our JavaScript variable by simply adding a third element within our array of arrays. And so in this case, this would be a three-dimensional vector. So once you then have defined vectors, right? So the next question is, how do we actually operate on the vectors? And so we talked about the two operations that have to be that a vector space has to be closed under, right? So the first operation that we talked about was vector addition. So on this slide is the definition for vector addition. So in the upper left here, like if we have 2 3-dimensional vectors, which are a and b, and we want to add them together, what vector addition will do is it'll go through each element and add each element of the 2 vectors together, and the resulting then 3 components will be expressed as a new vector for the result. And so visually, one way that is useful to think about vector addition visually is to imagine that if you took the vector A and you essentially plotted it in its space, and then at the end of that vector A, you plotted the resultant, or the second vector B, right? So sort of head to tail in this plotting fashion, that the resulting vector, which takes you from the sort of starting point of A to the ending point of your paired AB, would be the result of A plus B. So this is just one visual interpretation you can use when you're thinking about vector addition. And so in addition to this, vector addition is what's called commutative. So as a result of it, so commutative just means that A plus B is the same as B plus A in vector addition. And so visually, this corresponds to the fact that you can imagine this visual intuition as starting with either vector A, or you could start with vector B. And the resulting kind of pairing or combination of the 2 vectors when stacked, head to tail, will still have the same result of A plus B. Similarly, then vector subtraction follows the same basic rules. The only difference is that within vector subtraction, you essentially just imagine that the the terms within the secondary vector here would be negated. And so you can think about that visually as just flipping the direction of the vector that's being subtracted. And all of the other rules in the visual intuition will follow. So you can still stack the vectors, but you stack the flipped vector for the subtraction. All right. So another then useful set of properties that we can look at for vectors would be the magnitude, and then also describing what's called a unit vector. So the magnitude of the vector, once again, is the length of the vector within space. And so on this slide here, we're defining the mathematical definition for how you can calculate the magnitude of a vector. So in this first equation here, so the magnitude of this vector A, which is denoted by these double vertical lines, is defined as the square root of the sum of squares of each component of the vector. And so once you have the length, one interesting property that you can do with that length is you can then use it to modify the original vector to form what's called a unit vector. So if you take your original vector A and you divide each element by the magnitude that you calculated, you'll have what's called a unit vector, this A hat. And so a unit vector means that the magnitude of this direction is guaranteed to be 1. So by unit we mean 1. So it'll have the same direction as your original vector A, but the length is guaranteed to be 1. In addition, then the other operation that we described at this for vector spaces was scalar multiplication. So scalar multiplication is defined here. So if you have some scalar s and you want to multiply that by your vector A, you can simply multiply each individual component of A by that scalar s, and the resulting then vector is the result of the scalar multiplication. Okay, so another then useful operation that we can apply to vectors, which can be thought of as sort of analyzing like a property of the vector, is what's called the dot product. And so in this particular slide here, what we're showing is the equation for this dot product operation on vectors. So you can see what we do is defined here, and then an equivalent representation is defined with respect to the magnitudes of the two vectors. And so conceptually, what you can think about the dot product representing is it's measuring the similarity in the direction of the two vectors. And so that's one way that you can conceptually think about the dot product operation. So stepping forward, one other useful operation that you can perform on vectors is projections. And so, for example, sometimes it's useful if you have two vectors. So let's say you have a vector A shown in this figure here, and you have a vector B. It's sometimes useful to be able to calculate the projection of vector A onto B, which is illustrated by this vector A sub 1. And so what that looks like, right, is essentially when we say projection, what we mean is if you imagine taking the end point that's arrived at that vector A and projecting it along a perpendicular line onto this vector B. And so the resulting point there is what we refer to as the projection. And so it turns out that dot products can be used to calculate this vector A sub 1. So the equation is given here. And one other kind of way to think about this projection is you can imagine that this vector A1 is equivalent to the magnitude of A1 multiplied by the unit vector along B's direction. So a couple of questions then that you can think about for a second. So I'd recommend pausing the video here and sort of checking for your understanding, just to make sure that you're following. So the first question here is, what is the dot product of a vector with itself? And then the second question is, what is the dot product of two orthogonal vectors? So if you've paused and answered it, so if I move forward towards the answer, so the answer for what is the dot product of a vector with itself is it's the square of the vector magnitude. And so this follows if you sort of work through the equation that we looked at for dot products. And then on the second question, the dot product of two orthogonal vectors will be 0. because two orthogonal vectors, the angle between them is essentially as far from being the same as you can get. So two orthogonal vectors are pointing in orthogonal directions. Okay, so another set of checkpoint questions here. So once again, I'd recommend maybe pausing the video and making sure that you can answer both of these. So the first question is, so how many unit vectors are perpendicular to a two-dimensional vector? And the second then is, how many unit vectors are perpendicular to a three-dimensional vector? So now that you've had a chance to think about it, so we can walk through the answers. So in the case of the two-dimensional vector, there will be a total of 2 unit vectors perpendicular to that two-dimensional vector. And so the reason that there are 2 is you can imagine having an orthogonal direction pointing in what we could call like a positive and a negative direction. So this is illustrated in this figure by the red arrows here. And because we constrained it to be unit vectors, there can only be 2 unit vectors. There can't be an infinite number. And then on the second question, for how many unit vectors are perpendicular to a 3D vector, well, the answer is that there's an infinite number. So in this figure here, we're sort of illustrating a three-dimensional vector, of course, plotted on a two-dimensional slide. But if you imagine that this is a 3D space, then you could imagine sort of rotating a unit vector around this three-dimensional vector, and you'd result with this infinite set of vectors which would lie in a plane that's illustrated with this oval here. Okay. So one question that can often come up when you're working with vectors and you're working with some of the computation involving coordinate spaces, which we'll be looking at, is you'll have 2 vectors, and you'll want to be able to calculate what a new vector that's orthogonal to both of the existing vectors that you have given to you. And so this is where cross product comes in. So cross product does exactly that calculation. So given 2 vectors, you can calculate exactly a new vector C in this particular figure here that is orthogonal to both A and B, so both of the given vectors. And so in this, so in both these figures, so this A cross B is illustrated as the new vector orthogonal to A and orthogonal to B. And so this slide defines that calculation. In addition, another useful property of cross product is we can use it to relate linear and angular velocity. So, for example, if we have in this case a linear velocity of this point P, which is rotating about the point K, then we can directly calculate that the linear velocity of this point P based on the angular velocity crossed with the radius of rotation for this particular point. All right. So another then useful sort of JavaScript recommendation is for how we can implement matrices. So for matrices, if you remember, this would be, let's say, an m by n dimensional matrix. So in this particular case, this is a square matrix. So we have 4 rows and 4 columns, and so you can see we can implement it in a two-dimensional array of arrays. And this particular matrix is what is known as the identity matrix. And so whenever you see the identity matrix or a capital I within some notation, if you're reading either from some of the slides in the future or from material externals to the class, you'll see identity matrices quite frequently. What that denotes is that the diagonal elements here are all 1, and any off-diagonal terms are 0. So anytime you see an identity matrix, that is what we're referring to. So with this, then, this brings us to another kind of key topic within our use of linear algebra for this course, which is how to perform matrix vector multiplication. So if you remember back in the earlier portion of today's lecture when we were talking about systems of linear equations, right? What we said it could come down to is multiplying that vector A by some vector X to define our linear system. And so the way that we will then implement that form of a linear system is based on matrix vector multiplication. So this particular slide here is illustrating one sort of step, you could think about it, within the operation that goes into matrix vector multiplication. So what we're highlighting here is to perform a matrix vector multiplication. What you'll do is you'll take all the elements along the row of the input matrix, and you'll multiply them element-wise by each of the elements along the vector, and then sum the result to produce one output element at the corresponding row of the output vector. So in other words, this output, the first element in our output vector is going to be A times J plus B times K plus C times L. And so once again, you can think about that as sort of scanning down the row and scanning down the column in a corresponding fashion, right? So A and J are the first element of the row of the matrix, or the first element of the first row of the matrix, and the first element of the first row of the vector. B and K then are the second elements respectively. C and L are the third elements respectively. So you multiply each of those pairs and then you sum them together to produce your one output element. Another trick that is sometimes taught when you're just getting introduced to matrix multiplication is you can imagine scanning the row of the matrix with your left finger, so one by one, and at the same time scanning down the vector with your right finger. And as you do that, you can imagine multiplying each of the pairs and then summing the results to produce this one output. And so then to complete the matrix multiplication, what you would do is you would do that same process for the remaining, so for the second row of your input matrix, and then finally for the third row to produce your second and third output elements in this resulting output vector. And so I would recommend maybe pausing the video here and trying to work through this example based on what we talked about on the last slide. And so I'll wait a second so you can pause it and sort of test your understanding. So now that you've had a chance to think about it, if we step forward, so what we'll have is this will be the result. And so if we just sort of step through it, the way we're going to calculate this, right? So we're going to take 2 multiplied by 2 multiplied by 3, which would be 6, and then we'll add to that -1 multiplied by -4, which is +4. So we have 6 plus 4 is equal to 10, and then we can do the same mechanical process for the second row of our matrix. So we'll take 1 multiplied by 3 is 3, and 1 multiplied by -4 is -4. So 3 minus 4 is -1, and that's how we arrive at our second element in the output vector. Okay, so with that, so now that we sort of walked through the one example of how you can apply what's referred to as the row story for matrix vector multiplication, I'll just point out on this slide that there is another interpretation you could take, which is what's called a column story of matrix vector multiplication. And so in this particular interpretation, it's the same process. You're going to get the same result, but it's just a way of thinking about the result of the output as being what's called a linear combination of the matrices of the matrix columns. And so it's shown here, but from a mechanical standpoint, you'll get the same result. So this is really just for your reference if you're curious. So revisiting the cross product, now that we have this notion of matrix multiplication. So one kind of interesting fact is that you can actually implement the cross product using a matrix multiply operation if you construct your matrices in this form. So if you have a matrix A and you want to take the cross product if you have a vector A and you want to take the cross product with the vector B, you can perform that by first converting your vector A into this matrix here, so following this form, and then multiplying that matrix by the vector B that you wanted to take the cross product of. So this can be a useful fact sometimes. All right, so now once again, so now that we have matrix multiply, an understanding of matrix multiplication, now we can go back to the linear systems that we were talking about, and we can try and understand, and sort of convince ourselves that what we have defined in terms of matrix multiplication does in fact implement and correspond to to the linear system equations that we started with. And so as a reminder, the way that we had set this up in the earlier slides, where we said that a system of linear equations could be expressed as this matrix A multiplied by some vector of variables x, and that should be that would be equated to a column vector of elements B. And so graphically, then on the lower portion of this figure, we have just an arbitrary matrix A, an arbitrary vector x, and an arbitrary vector B. And so if you work out the matrix vector multiplication in the form that we just discussed on the past 3 slides, you'll actually find that our matrix multiplication does implement this linear system of equations. So you will have a set here of m equations that follow that linear form that we expect. So our matrix multiplication does in fact implement these linear systems of equations. Okay, so another then useful matrix that we'll be talking about a lot as the course moves forward is the one shown on the right here. Right, so we talked about the identity matrix. That is one matrix to kind of keep in mind. But this one on the right then is another one. And so this particular matrix, in fact, is what's called a translation matrix. And so where these terms tx, ty, and tz denote the translation offset that you're wanting to take in the x, y, and z directions of three-dimensional space. So, for example, like the one way to see how this does in fact correspond to a translation in this vector space is to try and work through this example. So if we take let's say we have some vector x, y, z, and we append a 1 to the end of the vector, and then perform this matrix multiplication. If you work through this example, what you'll be able to sort of see is how this does actually implement a translation of x, y, and z by tx, ty, and tz. So I'll pause for a second so you can pause the video and sort of work through it. And so once you've worked through it, you'll have found the answer, which is shown here, right? And so the reason that this is a translation is just that these element-wise translation elements tx, ty, tz are added to the original vector x, y, z. And so that corresponds, like we talked about in vector addition, to a translation. Okay, so this slide here, I'm not gonna go into this slide in too much detail, but on that topic of the column story interpretation of matrix multiplication, if you're interested, this slide has some visual interpretation that you can use for that, where again each column of the matrix is interpreted as a vector, and then we imagine this matrix multiply as a linear combination of those vectors. And so another then topic within matrix multiplication is how we can perform scalar matrix multiplication. So in this case, we have some scalar here, lambda, and we're going to multiply it by the matrix A. So the way that this operates is it's very similar to scalar vector multiplication. So we just multiply each individual element of the matrix by this scalar term. And so that then defines scalar multiplication. What's pointed out then on the bottom of the slide here is how you might see matrix multiplication described in text. So in this case, it's in LaTeX notation. This defines the same operation though of that we looked at before for matrix multiplication. But notationally, this is what you'll expect to see if you look in textbooks, for example. So another then kind of reiteration of matrix multiplication. So you can see in the upper right hand corner here we have this summary of the finger sweeping rule, which I mentioned about, where you can use your left and right hand fingers to sort of move through the row and column of two matrices in order to apply the multiplication. And so this follows the same form this follows the same mechanical process as what we looked at for matrix vector multiplication. The only difference with matrix multiplication is that instead of having a vector as this second element of the multiply, you have now a matrix. And so what you can think about that doing is you're just going to repeat that process of multiplying the row with the column but instead of having one column like we had in a vector, you just have multiple columns in this new matrix. So as a result, your output is going to not only have one column as a vector output, but it's going to have now a new column for each of the columns in your matrix B. And so, but again, you can apply that finger sweeping rule, or you can imagine taking each row of your matrix on the left hand side, doing a dot product with the column on the right hand side to produce one element of the output. So in this particular case, we're taking the third row of our input matrix, dot product with the fourth column of our right hand side matrix to produce the element at the third row and fourth column of our output. And so this is matrix multiplication. Working through an example of this is useful. If you have any questions about this, or notationally, if there's any concerns, feel free to reach out to the course staff, either on Slack or during our interactive session, and we'll be happy to work through some examples of this operation, or any of the ones that we've talked about. Okay, so a few then sort of reminders or summaries about matrix multiplication. So the first is that for matrix multiplication to be well defined, for it to actually be possible to implement, the number of columns of the matrix on the left hand side, which we'll call A, has to match the number of rows of the matrix on the right hand side, which we'll call B. And this is to ensure that dot product, that like row multiplied by column elements, is well defined. In addition, another kind of useful kind of trick you can remember is that you can directly calculate what the output size of a matrix multiplication will be based on the sizes of the left-hand side and right-hand side of the input matrices. So for example, if you have an m by k matrix multiplied by a k by n matrix, you know the output will have m rows and n columns based on the input having m rows on the left-hand side and n columns on the right-hand side. And in addition, I'll just point out that this first bullet, this number of columns of A must match the number of columns of B, is reflected by the fact that K and K must match. Those two sizes must be equal. And so one other important thing to remember is that unlike vector addition, matrix multiplication is not commutative. So performing A times B is not necessarily the same as performing B times A. There can be certain special cases where it is true, for example, like the identity multiplied by the identity, but in general, this is not true. So be sure to remember that if you're working through linear algebra proofs ever. So another few examples are shown on this slide. I'm not gonna step through each one, but I'll just point out once again that to do matrix multiplication, the process is you multiply. You take this dot product between the row of the left-hand side matrix and a column of the right-hand side matrix to produce one element in the output matrix. And so if you keep performing this row dot product with column, you'll keep adding elements to the output matrix until you've gone through each possible row column pair, and you'll end up with the full output matrix having been calculated. So here's another example that you can pause the video now and work through just to check that you're following our notation and you're following this concept of matrix multiplication. So I'll give you a chance to pause the video, and then I'll share the results. So the results in this particular case is shown here. I won't walk through it in this current lecture for the sake of time, but do feel free to come to office hours once again if there's any concerns about this. So another checkpoint question, which is good to think about, is this particular one here. So we have a set of matrix multiplications illustrated graphically. So in this particular figure, each of the pairs of boxes is meant to illustrate the size of two matrices that are attempted to be multiplied together. And the question is, out of this set of 9 matrices, which of them would be considered valid according to that requirement we had about the sizes matching up? So I'll pause here for a second so you can pause the video and think about it. So now that you've had a chance to look over the question here, so I'll display the results. So in this case, we're highlighting here the set of matrix multiplications that would be well defined and valid. And so once again, this is just based on the size of the number of columns of the left-hand side matrix with the number of rows of the right-hand side matrix. So for the sake of time, we have a few slides here, which I'm not going to go into too much detail because they're for the sake of time, but they'll be included in the PDF for your reference. So the first here is on interpreting matrices as projection operators from one coordinate system to another coordinate system. This slide here has a few useful matrix operations and well-defined matrices that are useful for referencing, just for your knowledge. And then this particular slide is a row story interpretation of matrix multiplication geometry, which again is useful for your reference, but for the sake of time, we will move forward. All right, so now we've covered like this definition of matrix multiplication. We've shown that it does in fact represent defining linear systems, but now we have this question of how can we solve linear systems given some defined matrix operator and a set of variables that are being related. And so in this particular case, the way to think about this is if we have this system of equations, right, ax equals b, how would we be able to solve for the variables x given this system? Because this is a very common problem within linear algebra, and it'll end up being very, very useful as we start to work with coordinate spaces in robotics. So it turns out that you can directly solve for this, right? If we could invert A, so if we could find some matrix that would invert the effect of A, then we could directly solve for x as being A inverse multiplied by the vector B. So the question then is, does this inverse matrix exist, and how can we decide if such an inverse exists? And so to answer that, it turns out we have to look at a property of the matrix known as its rank. And specifically, a matrix A is said to be invertible if it has full rank, where by rank we mean that the largest collection of linearly independent columns of A. So the rank of a matrix will be a number, and that number is defined as the largest collection of linearly independent columns of the matrix. And so if a matrix has full rank, that means that the number of linearly independent columns of A matches the dimension of the matrix A. And so once again, A is invertible if it has full rank. And so there then are given some matrix that does have full rank, there are different techniques that you can use to calculate the inverse. So one technique, for example, will be what's referred to as a decomposition approach. So this would include like LU decomposition, which you'll see within linear algebra, or sometimes within machine learning, you'll see LU decompositions used. But other decomposition approaches, so like Cholesky decomposition, we aren't gonna spend too much time on these approaches in this course. But if you're interested, this is an interesting topic that could be part of, for example, an advanced extension. But with that, there's this question, right, of are there cases where the inverse cannot be directly calculated, right? So can this decomposition approach always find an inverse? And the answer is no, because not all matrices that we're going to want to invert are going to have full rank. And so in these cases, is there some approach that we can use? And so it turns out, yes, we can approximate the inverse. And in terms of how we approximate it, it's using a technique known as the pseudo-inverse. And so the pseudo-inverse will be denoted by this by a matrix with a superscript plus. So that plus symbol denotes pseudo-inverse anytime you see that in this course. And this pseudo-inverse is doing what's called a least squares approximation of the inverse. So in particular, a pseudo-inverse is defined, like the definition of pseudo-inverse is defined on this slide. So for a matrix with some dimensions n by m with full rank, you can find a solution that minimizes the squared error. The left pseudo-inverse, on the other hand, is going to be for cases where the size of the number of rows is larger than the number of columns. And so you can see it's defined on this slide here. The right pseudo-inverse, on the other hand, is for cases where the number of rows is less than the number of columns, and it has a similar but slightly slightly distinct definition, which is shown on this slide. So these pseudo-inverse definitions here will be useful as we work with inverse kinematics in some of our upcoming projects. And so with that covers our linear algebra refresher. So that will conclude today's lecture. And I just want to point out that so in the next lecture we're going to start talking about forward kinematics. So we're going to start getting into how we can configure the robot structure within space using these topics that we talked about today. And so with that'll be the end for today. And I look forward to seeing you this week in the interactive sessions and during lab.